I will start with something that I found on the internet. You can see that this woman is paralyzed, has been paralyzed for many years, and then she was implanted some devices that allow her to control this robot by some type of implant, and then she can drink a coffee from a bottle which is controlled by the robot. And this introduces us into what now are called brain-machine interfaces, in which many electrodes are implanted in the head of a person or an animal. And basically, what is important to know is that the electrodes that are implanted need to transmit electrical pulses, and they need to be in contact with the nervous system of the person. And so by the signals that the brain can send to the machine through a very elaborated device, can control the arm of the robot. What is also important is that usually the electrodes you see here, this is a few microns, hundreds of microns electrode. So it's a very small electrode, but even though it is small, the scar which is created inside the brain of the implanted animal is very thick. So there is a lot of scar surrounding the electrode when it is implanted, because it's a foreign body, and so it is rejected by the person, by the nervous system, and so in practice the scar is insulating also adverse it can adverse the use of the electrodes. So a long time ago we started to think about this type of implants, and we decided to cover whatever can be considered an electrode with carbon forms, which can be either graphenes or nanotubes. And the main difference between these two systems is that graphene, of course, is flat, is 2D. The bundles of nanotubes can be three-dimensional. And so eventually, the modification of the electrodes through this deposition can lead to improved surface performance. And why we want to have improved performance? Because we want to have nanostructured interfaces, because we have a better physical chemical absorption with higher surface area. And then we want to produce nanocatalysis on these surfaces. And we can also use bio-inspired interfaces for cell growth and membranes. And we've been working for many years on carbon nanoforms like fullerenes, graphene, and carbon nanotubes, but also on carbon nanohorns and carbon nanocones, which are less popular forms of carbon. What is important to note about these materials is that they are very good electron transductors. This means that transduction of electrons from the surface to the solution or whatever it is absorbed on this surface is facilitated by the presence of these materials. So as already been mentioned, I am an organic chemist, and so we started by applying organic reactions to fullerenes and then to carbon nanotubes for the simple reason that the carbon nanotubes, which are usually very intractable, become much easier to handle if we can place organic moieties on the surface of nanotubes, because they become more soluble, they can be dissolved in solvents and can be translated to applications in many fields. The electron microscopy of the functionalized carbon nanotubes shows that the nanotubes now are much more individualized. So we can see individual carbon nanotubes here and there, and they are much cleaner than the starting material. We can play with organic chemistry, and we can place ammonium salts on carbon nanotubes. So this is a particularly interesting group because in this case, we completely reverse the hydrophobic nature of carbon nanotubes. So the nanotubes would be very hydrophobic and they would pack by van der Waals forces. But in our case, now we completely reverse, and so they become soluble in water. And so, for instance, because of the positive charges, we can attract DNA, which is negatively charged. And so we can use carbon nanotubes for delivery of DNAs and RNAs. You can see here, this is a molecular model. And here, for instance, you can see an electron microscopy in which bundles of carbon nanotubes positively charged, they attract this supercoiled DNA on the surface. And so eventually, there are several advantages of using functionalized carbon nanotubes and graphene because we can have improved solubility, we have an easier handling, we can add other functions, we can change the properties of the nanotubes of graphene, and also we can have improved safety of the resulting material. And so, for instance, when we started to work on carbon nanotubes for drug delivery, for instance, we discovered that if we label the nanotubes with a fluorescing agent like fluorescein, we can observe the nanotubes penetrating inside the cells, and we can see them into the cytoplasm of the cells by using confocal microscopy. So, and also we can elaborate the solutions of carbon nanotubes on the cell cultures, and so we can take slices and we can observe the entire cell to which nanotubes have been administered, and we can see nanotubes inside the cell. And we can also observe that in some cases, this is a photograph that takes the carbon nanotube, which is penetrating inside the cell. And so here you can see this is the cell membrane, this is inside the cell, this is outside, and we can clearly see that the nanotube is penetrating the cell wall without disturbing in what we have called needle-like mechanism of entering the cells. And so, for instance, we have used carbon nanotubes to study the labeled with indium-111 by using chemistry. So now the nanotubes are radioactive, and we can follow them inside the body of the animal. And so once they are administered, we can see this is the heart, and then initially it goes into the kidneys, and then from the kidneys to the bladder. So we can follow the metabolism of the nanotubes inside the animal in collaboration with Alberto Bianco and Costas Costarellos. And since we can clearly see that the animal is trying to excrete the nanotubes through the urines, and so if we collect the urines and we analyze them by electron microscopy, we can see the nanotubes in the urines. And so once we have made sure that we can use carbon nanotubes, they do not damage, they do not cause too much damage. We attached, for instance, an antibiotic, in this case amphotericin, together with a fluorophore, so we can follow the fate of the construct in the cells, and we can study the antibiotic activity of this amphotericin B. Also, we studied the attachment of methotrexate, which is an anti-cancer drug, and so we can play with many different molecules. We can attach whatever we want. Today, I will focus on two different topics, which is one, the use of carbon nanotubes and other materials for the production of water by electrocatalytic reduction of water. And the second topic will be the growth of neurons on carbon nanotubes for the curing of spinal cord injury. So This is a topic that was addressed very, very well by Marcus this morning. In practice, we want to apply small voltages in order to favor the production of hydrogen from water. And in doing this, we want to use some constructs that we produce now in our laboratories, which are made by carbon nanotubes surrounded by a layer of titanium oxide in which palladium nanoparticles have been encased. In this case, we have a triple phase active interface in which we have the three components which are all together. The titanium oxide is porous. We can play with the preparation. We can use palladium or platinum, and also the oxide can be modulated, can be titanium oxide, zirconium, or cerium. The work is being carried out in collaboration with Paolo Fornasiero in Trieste. In practice, they know how to prepare palladium or platinum nanoparticles surrounded initially by a weak ligand like dodecylamine, and then displaced by the use of this mercaptone decanoic acid. Now we have the palladium or platinum nanoparticles surrounded by acidic functions, and we can use the salt gel technique to generate a layer of titanium oxide around the nanoparticle. So basically, we end up, the carboxylic acids function as seeds for the salt gel processing, for the polymerization of titanium butoxides. And basically, we have now the platinum or palladium nanoparticle with the mercaptone decanoic acid, and then the layer of titanium oxide. And we have the possibility of tuning both the core, so we can change the metal or also the shell composition. And so we started by using oxidized carbon nanotubes. This is very easily made by treating carbon nanotubes, pristine carbon nanotubes with nitric acid and sulfuric acid. So these carboxylic functions will serve as seeds for the polymerization of the titanium butoxide. And so we can create these structures here. And again, we can tune both the metal or the oxide. And this is the type of material that we get. Here we can see the multi-wall carbon nanotubes that we have used as a starting material. Here we can see, I cannot see from here, but I assume you can see it. This must be titanium, this is zirconium, and this is cerium oxides. And as you can see, the nanotubes are nicely and homogeneously surrounded by this layer of the oxides. And as you can see here from this higher resolution image, we can see the carbon nanotube surrounded by, in this case, cerium oxide. And the cerium oxide is in the crystalline state, as you can see from this image. So together with Paolo, we decided to use this material for the water-gas shift reaction. So some few years ago, they were trying to do this reaction by using the palladium nanoparticles in titanium oxide, in cerium oxide. And what they found is that the catalyst decreases in potency very, very visibly. Then to restart the catalytic activity, they had to expose it to air for 10 minutes, and then the catalytic activity was again regained, but then again it decreased very quickly. So this was a problem, and we decided to use lower temperatures than 350 degrees by using the new constructs of palladium nanoparticles on cerium oxide on top of carbon nanotubes. As you can see here, the conversion is lower, but it's constant. It's 100 degrees less in temperature. So now we can see that even if we achieve an accelerated aging by heating at 450 for 6 hours, we keep the same catalytic activity. And so this is, of course, a much better behavior for this reaction by using carbon nanotubes. And what we expect from this, what we believe happening here is that the carbon nanotubes, we have an interface between the metal oxide, the metal nanoparticle, and the carbon nanotubes, which produce, in which the carbon nanotubes can facilitate the electron transfers, and so the charge separations are much more efficient when carbon nanotubes are present. We did more or less the same type of chemistry by using carbon nanocones. In this case, as you can see, we applied the same type of chemistry, so we could produce the carbon nanocones surrounded by a layer of titanium oxide and palladium nanoparticles. And here, in this case, we can clearly see this is the initial type of carbon nanocones, and this is after the reaction. So we can see that the homogeneous distribution of the metal oxide around the carbon nanocones, and here, in these beautiful TEM images, we can see the different elements which are present here. So it should be carbon, oxygen, titanium, and even the palladium. We can see the palladium nanoparticles, which are very nicely distributed around the nanocones. And again, together with the group of Paolo Fornasiero, we measured the catalytic activity in ethanol photoreforming for the production of hydrogen. And we can see that out of all the components, only the carbon nanocones on carbon nanotubes and heated at annealed at 350 degrees can produce a reasonable amount of hydrogen under irradiation. Another type of materials that we assembled is these two types of materials we produced. One is the standard oxidized carbon nanotubes. In this case, we applied reaction and we introduced the carboxylic functions here. And then we assembled the salt gel chemistry on top of the two materials by using carboxylic acids as seeds again. And in this case, the two materials differ only by the distance of the layer of titanium oxide on the surface of carbon nanotubes. So in this case, the contact is less efficient than in this case. But eventually, the two materials can be calcinated, and they will achieve, eventually will give rise to the same material after the annealing at 350 degrees. So we can check the morphology of the material. We can follow the carbon, the oxygen, and the titanium presence on carbon nanotubes. And we can also reconstruct a three-dimensional image in which we have the carbon nanotubes. We can see also the palladium nanoparticles and the titanium oxide layer. In this case, we are using this material for the electrochemical generation of, this is an electrolysis of water, which is favored by the presence of the catalyst. So if we compare the titanium oxide and palladium nanoparticles on carbon nanotubes against the titanium oxide and palladium nanoparticles, we can see that there is a difference, quite a difference in our potential, which favors the presence of carbon nanotubes. And here we can see again that the turnover frequency of this system, which includes the carbon nanotubes, is much, much higher than the simple catalyst without carbon nanotubes. So it is important to note that the presence of carbon nanotubes increases a lot the activity, catalytic activity of these materials. And also, as I mentioned before, if we have these two materials before calcination, have a much higher overpotential with respect to the calcinated material. The calcinated material is here. So the two materials become equivalent after calcination, which means that all the organic groups have gone away. And so the final material is relatively similar with much higher performance with respect to the original functionalized materials. Also, we can see that all the components, these are either the palladium on titanium oxide or only when all the components are assembled together, we can have these very high turnover frequencies. And if we compare our material with other materials which are top performing except of course platinum, which outperforms all the other materials, I couldn't place your material here, Marcus. We will try next time. It's worse. Okay, so we've been certified on the spot by the authority. So basically what happens here is that the titanium oxide has a high affinity for water, so by hydrogen bonds they are attracted here, and then the palladium nanoparticles can transfer the hydride to the protons, and so we generate hydrogen. Other materials that we are considering now are the carbon nanohorns. The beautiful aspect of carbon nanohorns is that they are very porous materials. So we reason that this material might be useful for the reduction of carbon dioxide to formates. And so we applied the same chemical reactions in order to achieve these type of structures. And again here, in collaboration with Lucia Nasi in Parma, we could obtain these beautiful TEM images where we can see the carbon element here, the titanium mapping, and then the palladium mapping. And again, you can clearly see the very homogeneous distribution of palladium inside the construct. This is still under study. We expect to see some reduction, but I know the picture here is much more complicated, so we will need to wait another few weeks or months. And so the conclusion of this part is that we can use all these carbon nanoforms which have different shape and different performance in order to use them as supports, active supports, because they are very electroactive, so they can transfer electrons very easily. And so charge transfer, electron transfer events occur very much easily on this type of carbon nanoforms. If we move to the other topic I wanted to discuss with you today, the use of carbon nanotubes towards curing spinal cord injuries. So this is a completely different topic in which we deal with an illness which is incredibly demanding in terms of efforts to solve this problem. And so when an accident occurs, the spinal cord is displaced, and inside the spinal cord there is are the nerves which can transmit the stimuli from the brain to the external organs. And so if the nerves are broken or displaced, then the electric communication is inhibited, and then we cannot control the organs. And so, for instance, there are illnesses called quadriplegia or paraplegia, which are very damaging diseases in which the person is completely or partially paralyzed. And what happens in these cases is that where the lesion occurs, where the injury occurs, there is a formation of scars, and the scars again are insulating, and so the electrical transmission through the nerves is completely inhibited. And so basically what we reasoned was that a long time ago, together with Laura Ballerini, who is a neurophysiologist in Trieste, we decided to place carbon nanotubes in the spinal cord injury because nanotubes can be metallic, and so they can help reconnect the two parts of the spinal cord if everything goes well. And so we had to start it from scratch. So we had to take a glass cover slip. We covered it with functionalized carbon nanotubes. We have a solution. Now we can make very homogeneous films on top of the glass. And then in order to anchor the nanotubes to the glass, we have to heat them to about 300 degrees. And now we have a layer of, very homogeneous layer of carbon nanotubes, which can be multi-layer, multi-wall carbon nanotubes, double-wall carbon nanotubes, or single-wall carbon nanotubes. And at this point, we have this surface on which we can deposit neuronal cells coming from hippocamp, so hippocampal neurons, and then we let them incubate for a couple of weeks. This is the layer of carbon nanotubes on the surface, and as you can see, it is very homogeneous. When we grow the neurons grow very well. So it looks like neurons have a very high affinity for carbon nanotubes. The morphology is exactly the same. It's the natural morphology. So they are completely identical to the reference neurons. The dendrites elongate very similarly. So from the morphological point of view, there is no difference between carbon nanotubes and the reference. However, if we enlarge this image and we look closer to here, we can see that that carbon nanotubes are present in tight contact with the neurons, either with the dendrites or the main soma, as you can see from here. So it looks like there is an intimate contact between carbon nanotubes and neurons, and this is also confirmed by other experiments in which we can see, for instance, this carbon nanotube is penetrating this dendrite, or even in this case where we can see that the morphology of neurons looks very much like carbon nanotubes when they elongate and become thinner. We can also do other experiments. We can cut the glass in a transversal way, and so now we have, this is the glass, this is the layer of carbon nanotubes, and this is the neuron, section of a neuron. And normally, the neuron doesn't touch the layer of carbon nanotubes, but in some cases, we can observe that carbon nanotubes can penetrate inside the cell, and so it looks very clearly that there is a tight contact, maybe electrical contact, between the neurons and the layer of carbon nanotubes. And what the neurophysiologists do, they use a technique which is called patch clamp, in which they use a micropipette, which is in contact with the main body of the neuron. And by using this micropipette, they can either register the electrical activity of the neurons, or they can stimulate the electrical activity. And so what we observed when we compared the electrical activity of the neurons on the control, so on pure glass or on carbon nanotubes, it looks very clear that the activity on carbon nanotubes is much enhanced. This is a measurement which is called postsynaptic currents. So these are the currents that one single neuron is sending to the other neurons surrounding. And these events are much more numerous in the case of carbon nanotubes. This is another way of measuring the electrical activity of the neurons. And as you can see also, in this case, these are called action potentials. Also, in this case, we can see that the number of events is much, much higher than in the control. So this indicates that there is a very strong affinity of neurons for carbon nanotubes, and also that there must be some sort of electrical contact because the electrical activity of the neurons is enhanced in the presence of carbon nanotubes. And so this was very promising, and so we decided to go further. And so we wanted to see whether, if we place, now we are not talking about single cells. We are discussing about entire slices of spinal cord. So these are complex elements. These are not single cells. And so in practice, what we want to see is whether if we place two slices of spinal cord at a distance by which they cannot communicate, if we can place a bridge in between the two, maybe we can restart communication between these two parts of the slices. And when we did this with our layer of carbon nanotubes, nothing happened. And so we were very disappointed, and we didn't know what to do. However, we reasoned that maybe going from, since we are discussing of more complex matrices, we have to go to more complex carbon nanotube constructs. And so we decided to use this type of carbon nanotubes, which are assembled in a sort of sponge. It's a black sponge which is very elastic and can be elongated, can be very easily manipulated. And so this is the SEM image of the sponge. As you can see, these nanotubes are strongly entangled, and the whole material is conducting. And if we deposit neurons in this cage, we can clearly see the neuronal cells adhering to the nanotubes. As you can see, it looks like they very much like it. And so here we can see this is the sponge which is attached to the glass. As you can see, this is the glass, and this is a three-dimensional sponge. This is the empty sponge, and this is the sponge in which nanotubes, neurons have been grown. In blue, you can see the nuclei of the neurons, and in blue, in green, you can see the dendrites. So the dendrites elongate in 3 dimensions, and you can also see from here, this is from top to bottom, the different layers of the sponge. This is the empty sponge. This is the full sponge with you can see the dendrons in 3 dimensions. This is from top to bottom, and we can clearly see that the neurons elongate in 3 dimensions. So now we can go to the experiment. So we can take the 2 slices, we can deposit them on this nanotube sponge, and then we can see what happened between these two from the electrical point of view. First of all, the morphology. This is the control. As a control, we use the glass, but covered with a material which is called chicken plasma, which is necessary for the spinal cord slices to grow. And in this case, we can see the nerves that grow from these spinal cord slices. They are very thick and long, but they don't try to contact the other spinal cord explant. And so in this case, in the case of carbon nanotubes, we can see that the morphology is completely different. Now the fibers between the 2 spinal cord slices are much thinner, but much more dense. So it looks like the morphology is completely different in the 2 cases. And so if we look at the activity, now we can see, we can register the spontaneous activity of the 2 slices. And as you can see, there is no whatever similarity between these two. So this means that the two slices do not communicate, because otherwise this would be synchronized. And if we stimulate one of these slices with electrical pulses, the same slices responds immediately, whereas the other doesn't look like it is doing anything. You can see here, this is the pulse, this is the response of one slice, but the other one doesn't respond. If we go to the carbon nanotube case, we can clearly see that already at the spontaneous activity level, we have complete synchronization. So the two slices are synchronized. If we excite one, stimulate one slice, the other one responds immediately. And so this means that the two slices now behave like a single organ, so like they were completely synchronized. And so, of course, this is a very important experiment, which is very promising in terms of future applications. But what happens, how this material is compatible with the nervous system? So I just remind you what I told you before. So the scars which are created by the electrode is very thick. And so we wanted to reproduce this with the animal. So we implanted the nanotube sponge in the brain of the animal. And this is the hole which is produced by the sponge. You don't see it because all the rest is labeled by fluorescence, but whereas the sponge does not fluoresce. But you have to imagine like we have the sponge in here. And this is the reference, the other hemisphere as a reference. As you can see, the scar is very, very small. In practice, there is almost no scar. Again, we can enlarge the images and see in these places what happens. And you can see that there is a very, very thin layer of scars in all these images. What is important also is that the sponge has been completely colonized by the nerve system, and so the nerves have elongated inside the sponge. And you can see it also from here. These are the nanotubes, and this is the living matter which is proceeding, and it's very well integrated. And you can see it's completely melted with the carbon nanotube sponge, as you can see also here. So it looks like the system, these carbon nanotube sponges are very much useful in terms of future applications for this incurable disease. And so we are currently using a device, this carbon nanotube sponge in the animal, and see if motility is recovered in the animal, in the injured animal. This is a work highly interdisciplinary. Besides the people that excellent postdocs and students in my lab, and the collaboration of Paolo Fornasiero in Trieste, we have used carbon nanotube sponges produced in Maurizio De Crescenzi in Roma, the electrochemistry in collaboration with Francesco Paolucci, the neurophysiology in collaboration with Laura Ballerini. I didn't speak about water splitting today, the high-resolution TEM with Lucia Nasi in Parma. And these are the sponsors, and I thank you for your kind attention.